Today starts. Hello, good morning. I believe I'm online. Good, great. So let's get on with and complete our general anatomy sessions. I think the audio on this system is better than it has been before. Like I said, our systemic anatomy, we had to cover 12 systems. Some books describe as 11, some as 13. It depends on how you divide it up. But like I said, the human organism works with all these so-called systems interacting seamlessly with each other like a single unit which has to survive in its environment, which has to grow and develop and live to its maximum potential, and which has to reproduce and create a next generation. These are the imperatives of an animal or a human biological life. And all systems work together to make this not only possible but as successful as possible in competition with other members of the same species, and definitely in balance and harmony with other species on the planet, some of which will become our food, some of which may become our predators or our prey. So if you think of the human biology as an animal evolution zoology phenomenon, our systems are very beautifully intertwined to bring about maximum efficiency and maximum comfort and safety and effectiveness in the environment and survivability for as long a lifetime or a life expectancy as possible. And these have been added as small steps in evolution in different systems, very disparate and diverse from each other, but always serving the organism as a whole. There's a whole bunch of beautifully written books on comparative anthropology, on social anthropology. I don't know if you've heard of Richard Dawkins. You should read things apart from pure science textbooks to get a better perspective of how all of life is served by the processes of evolution and interaction and planetary coexistence. We are, each of us is an ecosystem in ourselves, and that is brought about to survive in the larger ecosystems at different concentric levels. It's quite fascinating. Right now, in medicine, you won't have time for any of this. So concentrate on the science of what you need to know to function as a good doctor in your future. Let's come to the immune system. This again is something I borrowed off the net. I think the author is not acknowledged. I think it's one Dr. Lakshmi Giri or some Lakshmi Gupta, if I'm not mistaken. The spellings are, many of them are wrong. For example, organ, this should be organ, component organ. It's written as organ, which is, so please mind the spellings. I will expect that you'll have the common sense and basic IQ to be able to do this without much of a problem. All right. And when in doubt, please raise the doubt and or have it corrected through a reliable textbook, or you can ask any one of the staff who are taking classes with you. So here you can see the third point is endocrinology. Now that is not immune system. They are two completely different things as per the classical understanding. But we find that there are very many overlapping gray areas, interface areas. There is neurohormonal function. There is neuroimmune function. There is um, uh, hormonal interactions where the molecules have a multi-purpose kind of situation depending on what evolves. So these are at the cutting edge, at the front line of scientific experimentation and scientific discovery, publication, research. Your generation will also be doing a lot of work here. That's why this is the thing I wanted to deal with last, because the lines are not so clear, the lines of demarcation. Still, for purposes of understanding and holding it together in your head, it's good to think of the immune system as a whole bunch of stuff which is networked both as structure and function to defend the organism, the singular organism, against external attack by foreign cells or foreign proteins. This is brought about through a network of cells and cell products which are created with a particular design and structure in mind to bring about a certain kind of interaction which will result in a kind of defeat of the invading structures. They could be cells, living cells, or they could be cells of the body which have turned against themselves, like in cancers, or it could be a protein, a product of some other living system which has entered your body but is not compatible with its health, and therefore it gets engulfed and defeated or consumed and removed. So this uh, whole system also functions with a certain level of memory. If one attack has come in from a particular kind of protein, and it is dealt with there and then, that is one way of managing it. But a better, higher way of managing it is to remember that this thing has come in and might come in again, and therefore to create a standing army of materials which can recognize it even quicker and deal with it even quicker the next time it happens. So this memory, immune memory, is a very, very basic design element of how our immune system is put together, and we rely on it in healing. We rely on it by stimulating it in vaccination programs and so on. You will deal with immunology in a very big way in the second year in microbiology, but you must know that the system consists of so many components. There are primary organs of immunity and secondary organs. The primary ones are the ones where the first level of lymphocyte production takes place, which is bone marrow, and then differentiation or maturation or readiness for action takes place, which is again in bone marrow as well as in an organ called the thymus, which has a limited peak performance life. It is there in your body right from the beginning to the end, but its peak performance is happening in your very young life, where you're being primed to deal with all possible varieties of insult from the environment. So the thymus gives the name T to the T lymphocyte which it produces, and the bone marrow gives the name B to the B lymphocyte which it produces. The two of them are two different cell lines. We'll come to that. Coming from two different mother cells, blast cells, and the way they function is completely different from each other, but there is a coordinated cooperative way in which they attack foreign armies. So B will will deal with one way and T will deal with another way, and between the two of them they finish off the opposition, so to speak. So again, there is some amount of obviously some cellular signaling and communication which will be required to bring this about, and again some loops of control. This all at molecular levels and at single cell and clonal populations of cell levels, and how they bring it about is usually cascades of control. One interaction will happen like a chemical, like a chemistry equation. A plus B will become C plus D, and the output of that, the C, will impact something else, where X and Y will become Z, and then the output of that will become P, which will impact Q and R. And if any one of these little things is missing, the whole circuit will not be completed. So it's quite detailed. It is the way it is, and you'll learn about it next year. But you just remember that the primary organs we have in the body, which you will see in anatomy to some extent, will be bone marrow for the B lymphocyte line and thymus for the T lymphocyte line of defensive cells. The secondary organs are the ones where these basic lines, already produced lines of cells, will be housed or stored or multiply in numbers or grow in sophistication, maturation. Primary production is not happening there, which is why they are called secondary organs. So systemically, there are a very few hundred lymph nodes present in different groups in various parts of your body. There is this big organ called the spleen, which also has other functions, but is a very important immune organ. We have isolated lymphoid follicles in various places, especially related to the linings of the tubes which deal with external environment. Your respiratory system lining deals with external air all the time, right? 16 to 18 breaths a minute. So that lining has to have a protective population of lymphocytes waiting in case some other foreign antigens are going to invade and attack. So the follicles of or aggregate groups of a few thousand, few lakh lymphocytes will be available in a quiescent state just under the surface of the linings of these tubes. Similarly, gastrointestinal tract, from your mouth to your anus, the inside of your gastrointestinal tract is outside. It's the external environment. It's not you. You is the material, the stuff between your skin and the inside lining of your gastrointestinal tract. You're a tube within a tube, right? And that inside of that inner tube is actually external environment, because you're going to be putting in things and things are going to get eliminated, and what you put in from outside is foreign environment. So your whole gut associated lumen, the lining, has to have a protective barrier provided. So apart from its lining epithelium, which by itself has, by its tight intercellular junctions, has a seal against allowing in unwanted things, there is a layer of lymphocytes provided in groups. So we call that mucosa associated lymphoid tissue, MALT, M-A-L-T, right? And one variety of them is what is called a Peyer's patch in the small intestine. You would have heard about it. There are also organs apart from the spleen, such as the tonsils. It's a ring of lymphoid organs around the entry points of both the respiratory and the digestive system, which are primed in your pharynx area, oropharynx, nasopharynx, laryngopharynx area, to protect the apertures of the tubes which are going away, leading into the other systems. So we will see that those macroscopic lymphoid organs are called tonsils. We will look at that in the histology of each of this. As a system, you remember primary organs and secondary organs. Primary are the ones which give rise to the populations of cells, and secondary ones are the ones which house and modify and potentiate these populations of cells at various points of your life. They include large organs such as spleen and tonsils, and also lymph nodes located all over the body, and isolated smaller microscopic structures called lymphoid follicles, which are largely associated with the mucosa of the tracts of your systems which deal with the external environment. So the major organs, like I mentioned, are the thymus, which is located here in the anterior mediastinum, just under your sternum bone. The liver, which has a very important immune function. The bone marrow, already mentioned as a primary organ. Tonsils, which is around the throat area. Lymph nodes in the armpit, in the inguinal region, at joints, various places where your body flexures are there. Spleen, which is here, and blood itself, where the lymphocytes are floating around. Lymphocytes and other groups of WBCs. So the organs, primary lymphoid organs are bone marrow and thymus. Secondary are lymph nodes, wrong spelling, LYMPH. Spleen, mucosa, MUCOSA, mucosa associated lymphoid tissue, MALT, MALT. The cells we already mentioned, B lymphocytes and T lymphocytes, and non-killer cells. We will come across this in macro. I won't deal with it now. The granulocytes is one group of WBCs which are non-lymphocyte in origin, and they divide into three further subtypes: neutrophils, eosinophils, basophils. And you already know about this, and you will learn about it in the blood chapter of physiology. Phagocytic cells derived from our WBC groups are called monocytes, macrophages, and dendritic cells. They evolve or they arise as a response to stimulus from a foreign antigen. The cells of the immune system, like I was mentioning, when there is a stem cell, a blast mother cell in the bone marrow, the two basic main types it can divide into are called myeloid and lymphoid stem cells. The lymphoid one will only go and form lymphocytes through a lymphoblast stage, B type, T type, and natural killer cell. Did I say non-killer? I'm sorry. The NK means natural killer cell. So three types of lymphocytes coming from lymphoblasts, which come from a lymphoid stem cell. And these all are part of your WBC component of blood, the cellular component of blood. Plasma is the non-cellular component. The same blood stem cell could otherwise, if not into lymphoid, could differentiate into a myeloid stem cell, and from this all other groups of blood cells would arise. So that means it would have to become three streams. One type which will become a erythroblast and give rise to red blood cells, another type which would have to become a megakaryoblast and which will break up into platelets which will go into the clotting mechanism, and the myeloblast which will become the granulocyte series, that is your basophil, eosinophil, and neutrophil type of uh, WBCs which have granules in them. Lymphocyte series don't have granules in the cytoplasm. Granulocytes, as the name suggests, have granules in the cytoplasm. There are three types of those granules, which is why three types of cells. These plus these, all of them is equal to the white blood cells that you see floating around in the peripheral circulation, alongside of red blood cells and platelets, which are the components of mature blood. Now, I won't go into the stages. They will teach you about the evolution of the blood cell lines later. The function is, it is to protect against disease or against disease, period, which is mediated by potentially damaging foreign bodies. Could be foreign cells or foreign cell products. And the major function, of course, is a host agent interface protection. And for that, you have to be able to recognize who am I or who belongs to me and who doesn't. So the cell signals, the cellular recognition of self and non-self is basic to this. Right? If a WBC is in the environment of certain cells which do not belong to that particular individual, doesn't have the same genetic complement, does not have the same chromosomes, it has mechanisms on its surface through which is expressed through surface receptors, which will allow it to recognize that this thing does not belong to me. Then the next thing it has to do is, okay, it does not belong. Is it a potentially harmful thing, or can it be allowed to coexist and hang around? Because in our oral cavity, in many of our on our palms, in many of our systems, digestive tract, we have pockets of foreign species, commensal organisms, bacteria, and so on, which live there happily enough and do not interact with our immune system, do not offend us or attack us or invade us or threaten us, continue to make a living, sometimes consume, sometimes almost always consume nourishing things which we have consumed, and in return sometimes they are symbiotic and they create or they manufacture molecules which are useful to us, such as certain vitamins in our digestive tract. So our WBC system should be able to differentiate between a harmless commensal, COMMENSAL, and a potentially harmful foreign organism, very similar to but not a commensal in nature. So that's another whole bunch of learning. That's a whole bunch of exposure and learning that your WBCs have to do. And this whole learning, tuning, titrating process takes several years through childhood to mature. So your immune systems are not ready to go and fully fight with anything and everything from the environment from birth. It takes a long period of mild exposure, not too much. Too much will kill the baby, but not zero, because then you don't get exposed to a potential insult or danger. And if it happens in a large dose, a little later in life, you're completely unprepared because your WPCs have not been primed. So there is a via media, a golden mean, a balance point, where small amounts of exposure throughout childhood, repeat bouts of mild illness strengthens and builds up and potentiates the immune system and makes usually by the time of sexual maturity, which is adolescence, puberty, let's say 16 to 18 years of age, the immune system also kicks in with maximum capability and is then able to lead into young adulthood where you are at your peak of immune defense, along with the peak of almost all your other systems, right from your intellect to your muscular action to your digestive capacity to your respiratory capacity to your cardiac reserve. Everything is at peak in the young adult animal, including the immune defense, which is already ready and primed and able to ward off any foreign threats very quickly, very efficiently. So prevent pathogens from entering, eliminate any pathogens which may have already entered the body, and provide a group of memory cells so that a future infection from the same pathogen or disease causing agent can be dealt with. This is an assignment given to a school kid, I think. What is a pathogen? What is a purpose? What is a structure? And our two types of immunity are non-specific immunity and specific immunity. So non-specific is provided by, we already talked about integumentary system yesterday. So anything and everything which is outside of the skin is a foreign protein, that is, the barrier is provided by the skin itself. Anything which enters and which cannot be handled by us, which is not useful for our species to consume, will get handled through certain enzymatic proteins which have been provided. Then there is a molecule called interferon, which is provided, which is in the plasma. It is a dissolved molecule. It's not a cell. It's a product which non-specifically picks up and finishes off viruses and certain classes of pathogens. Specific immunity requires a recognition. Who are you? And I will remember you. And that is a whole process which is initiated, and then stages of it happen, and then a mature situation of it happens. The organs we already mentioned: tonsils and adenoids around the oral and nasal apertures, lymph nodes in various places, thymus in the chest, spleen in the abdomen. Peyer's patches are these mucosa-associated lymphoid tissue of the small intestine. Appendix itself is a lymphoid organ in some methods of understanding, but rather the lymphoid follicles of the protecting the lining of the appendix are the immune element. Bone marrow as a production site. Lymphatic vessels through which all these lymphocytes will flow. Then let's move on to endocrinology. Though, like I said, it's a completely independent, separate system, we consider it to be related because to some extent the master endocrine mechanisms also govern the master immune mechanisms. And we are still learning the levels of interaction. We still haven't got the whole story. So in the endocrine system, obviously in the brain, we have centers, the highest centers called the cortex, cerebellar cortex. And then below that, a whole diencephalon consisting of thalamus, hypothalamus, epithalamus, metathalamus, whatever. So that whole area is a subcortical highest center that we have, in which one called hypothalamus is the master endocrine regulator. And that hypothalamus first controls an organ we have called the pituitary gland, which is also housed within the cranial cavity in a small bony cave called the pituitary fossa. And this pituitary gland has two areas, an adenohypophysis and a neurohypophysis. And these secrete the regulating hormones of the various systems. Then in the brain itself, again as part of the diencephalon, we have a epithalamus area called the pineal gland, which also has an important function, particularly in setting our day-night circadian diurnal rhythms in sexual maturation and to some extent in control of the immune function, circulating immune function as the individual develops. Then we have the adrenal gland, already mentioned. With excretory system, I said there are these two adrenals at the upper pole of each of the kidneys, which secrete a whole bunch of molecules, which organic chemistry, which are steroid hormones, and which regulate our sugar, that is glucocorticoid metabolism, our mineral metabolism, as well as our sex steroid reproductive mechanisms. So this it does by influencing the gonads, the male gonad testicle and the ovary, which secrete a next level of hormones, partly in response to adrenal cortex stimulation and partly in response to higher reproductive centers, which are again available in the hypothalamus. Also regulated by regulating hormones of the pituitary gland. So between pituitary and adrenal, the governance of the gonads happens, of the testicle and the ovary, and the molecules floating in the blood are products of these two. So testicle produces testosterone, which dominates in the male circulation, and ovary secretes estrogen, which dominates in the female circulation, bringing about maturation and full function of the internal sex organ, that is your internal genitalia, which we talked about yesterday, of that specific gender in that particular person. But both genders have both the hormones. One or the other will dominate depending on what gender it is, and that is determined by the genetic composition of that individual, that is whether it's an XX individual or an XY individual. Then there is a very, very rare population of people, human beings, completely mature adult human beings, whose sexual sex chromosome composition is not clearly XX or XY, and they are associated with certain syndromes. There may be an extra X, there may be an extra Y, there may be partial deletions, there may be the chromosome, but it is not expressing itself in the gonad properly because there is a androgen insensitivity of the gonad, and so on. So these are all various dimensions of what we call intersex. It is not hermaphroditism. That medical hermaphroditism is a completely different and very, very, very rare phenomenon, where some of your cells are XX and some of your cells are XY, and therefore you may have one gonad each producing both. The individual may be able to produce both, but that's a very rare phenomenon where different levels of intersex happen depending on the expression of the genes. We'll learn about that in genetics, but you remember that testis and ovary are important endocrine organs, because apart from producing the cells of the reproductive series, they produce a hormone which support the action of those cells and which support the whole body organ. They are circulating in blood. So there's estrogen receptors in very many tissues. There are testosterone receptors in very many tissues, right from the vein to the bones to the muscles to everywhere, which will determine the bodily habitus of the individual. Testosterone will make a more masculine habitus. Habitus means the size, structure, and proportion, muscle, skeleton, shape, development of secondary sexual character, all of that will be determined by the circulating testosterone and similarly estrogen. So this is a whole bunch of separate function called reproduction brought about by the hormones of the endocrine system. Therefore, the gonads are both cell producing as well as hormone producing organs. Then we already mentioned the thymus, which we said is where the T cells, the thymus lymphocyte, the T lymphocytes are potentiated. And then you have the thyroid. Everybody knows where that is. It's a butterfly-shaped little organ in the front of your throat, and that produces a very important set of molecules called triiodothyronine and tetraiodothyronine, T3 and T4, otherwise simply called thyroxine. And these circulating levels are very important, keeping up all aspects of the metabolism. So thyroxine is essential to life. You die without it. And therefore you need to have a healthy, sufficient quantity of thyroxine circulating all the time, and this will get regulated by a thyroxine regulating hormone, again from a superior gland, which is the pituitary gland. Then we have the pancreas, which is basically a digestive gland, but it also has small populations of cells which offer which are not doing anything directly digesting, but which are secreting a very important hormone, which is endocrine in nature, which means that it is not going to be emptied into one particular space through a duct, but it is going to go into circulation, into the whole blood circulation, and go to each and every living cell in your body, and is going to impact cellular metabolism for each and every cell by allowing the entry of glucose into each and every cell, which is necessary to keep it alive. And this hormone is insulin. So you have hormones which have small, they're all in micrograms, picograms, nanograms, very small quantities, but they're such powerful molecules that when they go and they float around and they reach the target organ, a whole bunch of stuff is stimulated and happens, and they bring this about in a very inter-organized way with negative and feedback loops. Particularly, for example, in the ovary, we know that a monthly cycle has to be maintained for menstruation to happen, for ovum to mature, to be shed, then to be waiting for pregnancy. Fertilization doesn't happen, then again it has to undergo the 28-day cycle. For that, between your pituitary and your adrenal and your ovary and your hypothalamus above that, loops of control have to be set up. So like that, same thing with thyroid, it's a simpler loop. Same thing with thymus, pineal, and pancreas. So the small region of the brain is the hypothalamus. It is a releasing hormone producer, right? And also, apart from the endocrine function of controlling all the other endocrine organs, it also regulates body temperature through its secretions. We'll do that when we do neuroanatomy. Wrong spelling, pituitary, Pituitary. Take this as a quiz, as a what do they call that? Teaser, where you can let me see how many spelling mistakes you can catch. Yeah, so don't note down these spellings, but take the concept with you. So the pituitary gland is hanging down from the same hypothalamus area of the brain. Till here is brain. This is the gland. So the anterior part is going to be producing growth hormone, which affects all the growing things, bones, muscles, organs. It's going to produce prolactin, which will affect the development of the breast. The female is going to produce luteinizing hormone, which will impact the ovaries, and follicle stimulating hormone, which will impact the testes, but also the ovarian follicles. So both the testicular seminiferous tubules as well as the ovarian follicles will be impacted by this follicle stimulating hormone. These two will be therefore impacting the gonads, and the final result will be production of estrogen and testosterone, and a third molecule called progesterone, which is necessary particularly for the maintenance of pregnancy, for initiation as well as maintenance of pregnancy. Then it produces, the name itself is adrenocorticotropic hormone. So it's producing something which will impact the adrenal cortex and make it secrete the cortical hormones. These told you the steroid molecules which I mentioned. Then a thyroid stimulating hormone which will impact the thyroid gland. The posterior pituitary is not producing any hormones but is holding, it is storing hormones produced by the hypothalamus, and those two hormones come here and sit here and they get released from here, and these two are the vasopressin and oxytocin. Vasopressin is also called antidiuretic hormone, ADH, which impacts the kidneys. We told you kidney is not only an excretory organ but is also going to be involved in sodium potassium control, and that is done under the influence of this molecule called ADH, which is produced in hypothalamus, stored in posterior pituitary, released into circulation, will come to the nephrons, and in the nephrons it will act upon the way filtration will happen in the glomerulus. Similarly, oxytocin will again produced somewhere else, stored in the posterior pituitary, will come and it will impact the release of milk from the breasts in a pregnant lactating situation, and will also impact the uterus, allowing the myometrium to become more sensitive to contractions. This is a very important hormone for the OBG, for the whole obstetrics gynecology segment. But even otherwise, even boys, everybody has oxytocin floating in their systems. So it is also considered it has been called a bonding hormone. It is released in emotional relationship interplay, and is important in the male female bonding to keep together potential parents of that baby which will result from that pregnancy. So the loops are not only impacting the biochemistry of all your target organs, but also the emotion back to the hypothalamus, where behaviors, animal behaviors will be impacted. Small quantity, small size molecules, extremely powerful, extremely diverse, extremely long impact molecules. Okay, the pineal gland is a little gland, tiny little thing at the back of the thalamus, which secretes and stores this melatonin and serotonin, two molecules, which operate on the brain. The output is going to impact it within the cerebral circulation. It is going to float all over the body in your blood, but the target which will respond to it is your brain, and it will set up mechanisms which will make puberty happen over a period of years, right? And over a period of hours, days, and minutes, it also influences the mood of that individual animal. That is brought about more by serotonin. Melatonin is a sunlight responding molecule, right? And therefore the timing of day and night and the amount of exposure the animal gets to sunlight will influence the way this acts, and therefore influences the mood. I think you might have noticed that if you don't see sun for 3-4 days, your whole metabolism tends to be a little sluggish and depressed, and you may not be very enthused about doing many things. Whereas you have one sunny bright day and life looks better. I don't know if you know, try to notice it next time. Those countries where individuals, people have to stay in dark periods, like Scandinavian, Arctic Circle countries, they have to provide artificial light with a good bunch of UV to keep their citizens in a more perked up, active, positive, let's do something kind of state. Because the lack of sunlight is a big deal for the human species. Okay, that's just one aside. What you need to remember is that the pineal is doing important things, and how it's mediating it is via melatonin and serotonin molecules. The thymus, which is there in your anterior chest region, has a medulla and a cortex. We'll look at it in histology. We'll see the gland and we'll see how it is, what the microarchitecture is like. But what we do know is that there are thymocytes which have so many subspecies of cell populations which they give rise to, like 2, 4, 8, 3, 6, 5. I mean, like at least 8 to 9 series of cells, and they go and do different things. The medulla matures the thymocytes and converts them into an active format, then releases them into the peripheral blood, where the T cell compartment, the thymus cell compartment of peripheral blood, will have differentiated clone populations of cells such as suppressor, cytotoxic T cells, helper T cells, which again are further classified into inducer and suppressor inducer. And we know that all this, complex levels and generations and populations of cells are necessary to be able to fine tune your immune response depending on what your earlier exposure to a potential disease agent is. And like I said, we're still learning, and we have picked up a lot, particularly through the disease called HIV/AIDS. We got to know a lot about how our immune system addresses a situation where your own cells, your own populations of cells become helpless, they become inactivated, they become suppressed to a point that they become incapable of producing sufficient numbers. So they go off like into a like a trance, in unable to respond state, and then you're a free for all for anything and everybody, anything, any other foreign species which wants to make a home inside you, which is why HIV/AIDS was such a killer, because not because by itself that virus is going to kill your cells, but because it inactivates all your T cells, so many types of T cells, and therefore you are not able to protect yourself either from an internal cancer cell, which is why many patients of AIDS die of tumors which would have been otherwise cleared up, eaten up, phagocytosed by these CD cells if you had sufficient numbers of them. Or they get attacked by small random infections which you wouldn't even have bothered about if you are sufficiently immune capable. And now you are otherwise a proper full-fledged human being, but you have no immunity, and therefore every simple small infection can flare and cause havoc inside your systems, particularly respiratory infections. So we saw that over a period of 2 decades now, more than that, 4 decades now. It started in the late 80s, early 90s, if I remember right. It taught us a lot about how these different generations of CD cells work with each other, against each other, in cooperation with each other. And any one foreign pathogenic process has the capacity to knock it off, and therefore where we can attack the attacker and defeat it. So thymus gland, okay, important immune organ. We've found a great deal more respect for this gland in later medical science. Earlier we didn't think much about it. So it is large in infants, in small children, and its whole function is almost completed by the time you're an adult. It has 2 lobes. It secretes an hormone called thymosin, and it works on with T lymphocytes, promotes the production and maturation of these T lymphocytes. Thyroid gland, we said, is in the front of the throat, produces T3, T4, and a cell called, it has cells which also produce a third hormone called calcitonin. Then you have the pancreas, we said, which has insulin, but it also has beta cells produce insulin, but there also are alpha and delta cells inside these islets of Langerhans, which is the endocrine component of the otherwise digestive gland called pancreas. And glucagon, vasoactive intestinal polypeptide, and somatostatin are the other hormones produced by it. Adrenal gland, we already said there is a cortex and there is a medulla. The adrenocorticotropic hormone from the pituitary stimulates the cortex and makes the zona glomerulosa produce mineralocorticoids, zona fasciculata produce glucocorticoids, zona reticularis produce androgens, estrogens. And mineralocorticoids are also contributed by fasciculata and reticularis. That is a new finding. We used to earlier differentiate glomerulosa, fasciculata, reticularis as 3 different types of hormones, but now we know that the arrangement of the cells is in small ovoid groups, is in slabs or sheets, and is in a network pattern. But all the cells have the capacity to produce all the output hormones. Largely glomerulosa will give you the mineralocorticoids, largely fasciculata will give you the glucocorticoids, and reticularis the sex steroids. The medulla is not an endocrine organ at all. The adrenal medulla is rather a sympathetic ganglion. It's like a autonomic nervous system component. So adrenal medulla and adrenal cortex are part of the same organ, but they actually came from 2 different places. And they do 2 completely different things, and they almost don't talk to each other in the sense that they do not have to interact with each other to produce their output. But they share the same blood supply and the same nerve networks, which is why anatomy is very important. So the medulla produces molecules called catecholamines, epinephrine, norepinephrine, and dopamine. Technically, these are neurotransmitters, but they're not only there for neural or neuromuscular action. Dopamine is important in mood and in influencing activities of certain other organs. So a word called neurohormone was evolved for those molecules which work like hormones in some places, which work like neurotransmitters in some places, which they seem to have a multi-purpose kind of effect. And epinephrine, norepinephrine, you'll see, are very, very important molecules for us. They're very, very important for the musculoskeletal system. They're very, very important for the cardiovascular system. They keep up our blood pressure. But they are also important output of the adrenal medulla as part of the autonomic nervous system controls of your unconscious functions, which is happening with your visceral muscle and your cardiac muscle. So the medulla can be ignored as far as or can't be ignored, can be considered a very minor contributor. It's the adrenal cortex, which is the major uh, endocrine organ. Ovaries we already talked about. It is going to be influenced by follicle stimulating and luteinizing hormone. Ovary will produce estrogen and progesterone, and this is what they do. I mean, let's not go. We'll anyway do all these details in the local place when we study that organ in gross anatomy and when we study the organ in histology, both ways. We said the testis secretes testosterone through a certain kind of cell called Leydig cells or interstitial cells. So the cells which are creating the gametes, the haploid male gametes, that is the spermatozoa, are different. And the cells which secrete the hormone, the endocrine cells, are different, but they're all housed within the same organ called the testis. So that covers the entirety of the endocrine system. We talked about lymphoid tissue and lymphoid or immune system as a bunch of materials, cells, tissues, and processes which bring about defense of the individual organism against any potential possible threat from the external environment mainly, but also against the internal environment in the sense that if any of your individual, you have a zillion cells, if any of them go beyond the restrictive controls of your metabolism and your self-governance, they can create copies of themselves which will dominate and overpower the nourishment available for the remaining normal tissue. And that is called malignancy. That transformation where a cell line or a cell group doesn't accept this organism's control systems anymore. Now our immune systems, our patrolling lymphocytes, are capable of recognizing a cell which has undergone this transformation, right? Which is undergoing a metaplasia. We will learn these words next year in pathology, but it means that the cell division mitosis is going out of control, and the daughter cells, which are now no longer following the rules, are able to be recognized by some of the patrolling immune cells that we have, and they are immediately engulfed, killed, and finished off. So our immune system is defending us against external as well as internal invaders, which are not towing the line, which are not following the rules. It's very, very important to remember that our internal sentinels, surveillance systems are very important. Otherwise, many of us, the species even would not last long enough to reproduce and make new generations of itself and become a very most successful species on the planet. Because its own cellular transformations. See, when mitosis happens, when cell division happens, there's a good chance by random probability that some of those cell divisions will result in a metaplasia, a cell line where some genetic mistake has happened, right, in the separation of the daughter cells, and that aberrant wrong genetics daughter cell can then make multiple copies of itself. It can go aggressive and behave like a foreign agent or a foreign organism within the parent organism, and that's what is. I mean, if you take 1,000 cell divisions, you take 1 million cell divisions which are happening in your body all the time. A few or a few hundred can go wrong, right? Mistakes happen. So if we didn't have the surveillance system, each of those mistakes can become a potential life threat or disease threat, right? So it's very important to remember that Our immune defense is, of course, largely geared to the external environment because that's where the organism is maximum threatened by, but also towards the internal policing, like, stay in line, don't get too aggressive, don't work against the master, which is the whole organism, right? And the endocrine system is a completely different mechanism and set of organs, very disparate, far away from each other, not connected with anything with each other except via the circulation, where they empty their product into the circulating blood, and that is a communicating medium which keeps the other things responding, and which brings back information to the higher endocrine control center that, oh, we wanted this much of thyroxine, this much was produced, action is happening, we may need a little more, or this is probably now enough, we need to shut off the stimulus. So then TSH will come down, therefore T3 T4 will come down, so that regulating loop will be brought into place. Secrete, don't secrete, right? And so on and so forth. In response to various things. So it's not only pituitary which gives the orders. The pituitary will respond to signals and information coming in from many areas. Pituitary will respond to hypothalamus. Hypothalamus is connected to neural circuits. So sensations and information coming in through the nervous system will get integrated, along with molecular information coming in from the circulatory system, right? And to some extent, top influence or higher orders coming in from higher centers. A very complex and multi-level control there, but it keeps your body singing, working beautifully in your favor without your conscious interference. So that brings us to the end of all of systemic anatomy. I hope you can hold this whole thing together in your head enough to be able to now get into region by region. Now we will only look at hand or neck or foot, right? And in that, all 12 system components are there in each region of your body. And they're already there, they're already placed there in certain juxtaposition and relationship to each other, sharing certain things, right? Certain responsibilities, certain jobs, certain supplies, just the space, sometimes the functions. In that area, your your live patient will come to you and say, there is something wrong with this place of my body. He doesn't know, you're supposed to know what all could be there. Therefore, we will go from surface to deep. We will lay it open layer by layer and we'll say, oh, at this level this is there, at this level this is there, at this level this is there. In the background is your whole systemic anatomy. In the foreground is the regional anatomy of what you're dealing with. And you'll put it all together and come to some conclusion and offer some help and hopefully heal that patient of yours and send them away well. Okay, so we'll close this class. We're done for this week. Next week we'll start upper limb. I still haven't got any information from the principal's office about when you can come for practicals. I suspect it won't be in the next coming month of March. Maybe you will be allowed on campus in April. So we'll organize in such a way that at least we can show you some pictures of the dissections, or we'll try if I can get create some videos, or at least I can direct you to websites where some nice videos are available. And you get started with that. So when you come on campus, we'll quickly do a revision and catch up so that your practical sessions and whatever theory we cover in March will come parallel with each other. We will come up to speed. Okay, so have a nice weekend and we'll see you on Monday.